So what is perceptron algorithm states? The value y equal to 1 if the value wx plus b is greater than 0. Here w stands for weight vector and x stands for input vector and b stands for bias. So once we will calculate this value, the value is greater than 0, then it classifies the data as 1. Otherwise, if it is less than or equal to 0, it classifies the data 0. This is basis on our textbook. In some other textbooks, they can take this as a positive and this as a negative. So some people will refer this as a 1 and this as a -1. So we will follow our textbook. So Simon Hacking textbook. So here we are representing the data. We are classifying the data. If it is greater than 0 as a 1, if it is less than or equal to 0, it belongs to the class 0. So this is a simple perceptron, single layer perceptron algorithm. And also we have to remember the neural networks learning steps. So actually neural networks have adaptive learning. So learn itself, and we also need to remember the steps. Initialize weight. So initially we have to initialize the weight values and bias value. So normally in neural network, weight value initialized randomly. Bias, we can choose the bias value. And after that, so forward propagate all the values layer by layer towards up to output layer. So next, check the error. So error means difference between the predicted output and actual output or actual response from the neural network. So next, if error is optimized, okay, no need to adjust the weights in a neural network. If error is not optimized, we have to back propagate and we have to adjust weights. Okay, weights and bias in single layer perceptron mechanism, and we have to repeat all this process for all training examples, for all epochs. We can say epochs. Epoch is nothing but one complete iteration is called epoch. Okay, so remember these 5 steps: initialize weight values and bias, forward propagate values, check the error. Here error equal to that predicted output minus actual output, or we can say desired output minus y. So if the error is optimized or minimized, or it is a local minimized value, so no need to propagate the values backward, no need to adjust the weights. If the value is not optimized, we have to adjust the weights and bias. So we have to repeat the process for all training examples. So now we will go through the AND gate. So AND gate is a logical gate, and all of you know that the truth table of AND gate. So here this is the truth table of AND gate A and B. So output value is 0. So here A value is 0, B value is 0, output value is 0. Okay, and here you have to remember, so this equation, so this values A is 1 and B is 1, 1. So the output 1 if only if A and B are 1s, then only the output of AND gate returns 1. Okay, so here similarly the value is 0 if and only if both A and B are zeros, then the output value is zeros. Okay, here we can consider A and B are 2 node values x1 and x2. Okay, see this value x1 is 0, x2 is 0, the network value you must get the value 0. x1 is 0, x2 is 1, you get the neural network neuron value or perceptron value must be 0. Okay, similarly 1 and 0, the value is 0. and 1 you will get the value 1. Then only our neural network representation is correct. Okay, if the values are not getting correct means there is error, and at the same time we have to update the weights. Okay, how is the process? I will explain slowly, so try to understand from here, it is very important. So the question is, what are the weights and bias for and perceptron? Okay, so here this is the normal neural network representation for two nodes x1 and x2. Every node has internet connection, interconnection, and this interconnection, okay, associated with weight 1 and weight 2. This is a bias value, and here y is the output. This we can say uh, linear combiner for AND gate representation. Okay, now here for neural network representation, we can calculate the sum of dot products. So here x1 w1, x1 times w1 and x2 times w2, these two we can call it as a dot products, and we are summing these dot products and we are adding bias to the sum of dot products. Okay, this we can call it as a net input calculated value. So this we can call it as a net input calculated value. After that we will apply activation function, or we can say hard limiting on this value. Then it decides, it limits the output value, whether it belongs to the output belongs to the 1 or output belongs to the 0. This is the representation of neuron. Okay, so now you can see row 1. So row 1, so here just you go through the and logical gate. This is row 1 and this is row 2, this is row 3 and this is row 4. Okay, row 1 is, so x1 is 0 and x2 is 0. Then what about weight and bias values? Just you can come down here. We are assuming the initializing weight values, weight 1 and weight 2 as one. Here only assumption. So mathematically we can write, consider weight 1 weight 2 equal to 1 and bias as -1. Okay, then you can substitute these values into this equation. This equation we can say equation 1. Okay, so then we will get x1 times 1 plus x2 times 1 minus 1. So that is equal to x1 plus x2 minus 1. This is the final equation. Okay, now passing the first row of the AND logic table. Okay, so what is the first row of values? 0 and 0. x1 is 0 and x2 0. So then we get 0 plus 0 minus 1. Okay, here the total value is -1. So that is less than or equal to 0. Then it classifies the output is 0. Okay, so just go through the logical gate. So we try to find out the value, output value is 0. Now what we got in neuron, if you substitute node value 0 and a node value 0, then we got 0. So then this is correct. Okay, this process is correct at row 1. Okay, so now we will go through the from the perceptron rule. If x plus b less than or equal to 0, because -1 is always less than or equal to 0, then the output value is 0 according to perceptron rule. Okay, so hence here the value is optimized. So here no need for back propagation. So that means no need for to update weight and bias values. So now we will go for row 2. x1 is 0 and x2 is 1. Okay, so now here x1 is 0 and x2 is 1. So you substitute in equation 1 x1 plus w1 times x1 plus w2 times x2 plus b. Already we assumed weights are 1 1. So now you get the equation x1 plus 2 x2 minus 1. So this equation you can substitute 0 and 1 values. You will get 0 plus 1 minus 1 equal to 0. So here 0 plus 1 is 1, 1 minus 1 is 0. So for the perceptron rule, x plus b less than or equal to 0, then the output is 0. So this row is also output is also correct, and the output is 0 for the AND gate also. Just compare with row 2 from the AND gate. So here also output 0. Next we will go through the row 3. So here x1 is 1 and x2 is 0. So just again you go through the row 3. Here I skipped row 3, and you will get the same answer, 1 plus 0 minus 1. So 1 plus 0 is 1, 1 minus 1 is 0. So definitely it is less than or equal to 0. So according to Perceptron, the value is equal to 0 means you will get the output value 0. So same value, that's why I skipped here row 3. I hope you understand this point. Okay, now row 4. So x1 equal to 1 and x2 equal to 1. I substitute these values in the equation x1 plus x2 minus 1. So here 1 plus 1 is 2, 2 minus 1 equal to 1. So that means again the perceptron rule, if the value is greater than 0, the output value is equal to 1. So still it is valid and this is correct. So here therefore we can conclude the model to achieve AND gate using perceptron algorithm. And for every operation we got the correct values according to our assumed values. So here I assumed weight 1 is 1 and weight 2 is 1 and bias is minus 1, and we are taking the input values x1, logical table representation values x1 and x2, because we are taking two input values. There are four choices, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and we substitute all these values in perceptron formula and perceptron network. So then we got all the output values correct. So now we are representing the AND gate perceptron representation here. Just you can see bias I assumed as minus 1, weight I assumed as 1, and weight 2 I assumed as 1, and x1 and x2 are 0, 0, 0, 1, 1, 0, 1, 1. So for every operation it gives it classifies the data either 0 or 1. Here we did not update any weight values or bias values, okay, because we got all correct values. If you have a all correct values, then that means your optimized values, no need to back propagate values or no need to update the free parameters, weights and bias. This is unrepresentation of and neuron representation using perceptron algorithm.